G'day everyone, welcome back to another video. So again, continuing on with our linear modeling unit, we're going to start looking at additional constraints. So we just practice shading our feasible regions with a couple of constraints, usually our x and our y are greater than or equal to 0, but that might not always be the case. So what we're going to do, we're going to think back to our sausage roll in our chip question. So I've just put it back here as a bit of context. So remember, this is our, that's a drawing, there we go, laser. So chips is my y, sausage rolls are my x. And we have these three conditions here. So 3x plus 6y has to be less than or equal to 24. That's this line here. And x and y both have to be greater than or equal to 0. But what if we were told that we need at least 2 sausage rolls and at least 1 tray of chips? What do the inequalities in our shaded region become then? So we need to look at a new condition on my x and my y. So remember, sausage rolls is x, so we need x to be greater than or equal to 2, so at least 2 sausage rolls. And we need y to be greater than or equal to 1, so at least 1 tray of chips. Now, to graph these inequalities for x, we need a line where all of my x's are equal to 2. Now, so we go to x equals 2, and we draw a vertical line through that point, so x equals 2. And same for y equals 1, so that is the coordinate where every point has a y value equal to 1. So that's a horizontal line through y equals 1. Now I've already put my equation 3x plus 6y equals 24 on there. Now we need to look at our shaded region, so our feasible region. So remember, it has to be above x equals 2, above y equals 1, but below 3x plus 6y equals 24. So above y equals 1 would be up there, above x equals 2 would be above there, and below 24 would be there. So it's actually this region in here. So my feasible region has gotten much smaller, if you can remember back to last time, okay? So we're looking at different inequalities of x, y, and my equation, and we're changing the shape of our feasible region, all right? So just a bit of a definition. So remember, our shaded feasible region is also called a simplex. So if you're asked to sketch a simplex, this is what we are looking for. So this whole picture here with our shaded region, labeled equations, and nice scaled labeled axes. So let's do an example together. Sketch the simplex defined by y is less than or equal to 10, x is less than or equal to 7, and 2x plus 3y is greater than or equal to 18. Now, these two are very easy to graph. This one, not so much. So we need to find our x-intercept and our y-intercept. So remember, y-intercept or x-intercept when y equals 0. So 2x is equal to 18. So that means x is equal to 9. Then we also have when x equals 0, 3y is equal to 18. And that means y is equal to 6. So we've got our x-intercept and our y-intercept. Let's graph those. So x equals 9, y equals 6. So let's just put a line through those 2 points there. Label our equation. So so we've got 2x plus 3y is equal to 18. Now let's have a look at our x and y condition. So x has to be less than or equal to 7. So we need to graph our line of x equals 7. Nice and straight, I can do that. So x equals 7. So all of these points along here have x equals 7. And then y was less than or equal to 10. So we go to 10 and we graph our y equals 10 equation. Now we have, let me just move this guy down here. So we need to be below our x and y conditions, but above our 2x plus 3y 18 line. So that means our shaded or our simplex is this box in here. Okay, so it satisfies all of our conditions. All right. So really key that we're graphing the right spots for our x and my y constraints, and then looking at our simplex again, all right? Hopefully this has been helpful, and we'll see you guys in the next one. Thank you.